Hey everybody, it's my first time in Africa. Such a pleasure to be here. I'm from Greece, by the way. I know my name is Freddie, doesn't sound very Greek. It's actually Alfredo, but that's because my mom is Brazilian. She's from Sao Paulo, and this is not too strange to me. I had a bit of a deja vu because when she moved to Greece, she was still practicing her religion, which was she was from Pentecostal church. So she took me to a few sermons, quite a few of them, when I was in my teens. So when I came in here with the car and then I heard all the singing, I thought, wow, this is like it feels familiar somehow, right? I'm Christian Orthodox, by the way. I don't practice, but I much prefer this kind of environment. Oh, okay. But through science, and this is what I do. Before joining Aspia, I'm going to cut this short in a little bit. I was at Oxford University. I was a scientist. I worked in a few companies, and what I do really is computer science and AI. And I'm going to show you how AI can be used in this mission. I've worked a lot with different kinds of applications, but the last 6 years I've worked with satellite data a lot and seeing how that can benefit humanity. And through this work, I've had a new appreciation for light. Now, I'm sure everybody here knows the importance of light, right? It's the first thing that's mentioned in the Bible, right? Let there be light. It's the very first thing that was given to us by God. And the very first thing that existed in this universe. Let's zoom in a little bit. 500 meters that way, in a farm called Bethel. What you're seeing here is a satellite's viewpoint of Bethel across the entirety of 2023. Every day, there's a picture there. Clouds and all. It's really interesting, right? It's like having a yearly wrap of the entire farm. It's kind of like in the center. You can see the development that is happening, how the crops are changing in a very granular way. This is great. It's like, okay, we have a snapshot, we have a video of what is happening on every farm on the earth. So what? Like, how we have this gift. How can we make the best use of it? How can we benefit from this gift? We want to know what is happening on the earth. And what you're observing, this video, is like data. And that data tells us something about a phenomenon, a very important phenomenon to this people here, which is growth. And how can we optimize the growth of our crops? Where do we plant? There's a story that has been told by the data. And we can use the data to extract that story, and we use AI to extract that story. So we can do this around the earth 24/7. We don't have enough people on the ground to be able to monitor up close these things. So what Earth observation is doing, and the gift of light, is able to fill in those gaps, this missing data, because we don't have enough people on the ground. And also turn uncertainty into less certainty or more certainty about what we're trying to do here. So there's 3 pillars here that I want to build in our use case. One is a remote monitoring, or how we call it remote sensing, but think of it as a remote monitoring, which is everything about the sensors up in the sky and the data that they build for us. The AI is the second pillar, which is the mechanism through which we allow computers to automate these tasks that we want to do. And eventually, how does it come back to us? How does it benefit us as humans? For science, for farming, for other very important uses. Anything has to do with situational awareness. By the way, how are we doing on time? Can I ask? It's going to be over there. Yeah. So we have until... Quarter to 11. All right. Okay. So I have about 20. Okay. So, you, sir. You. Okay. Look at me. Okay. Can you tell how high, how tall I am? Can you estimate? Give me a number.
1.7.
Okay. It's not far. It's not bad. It's a good guess. You, sir. You, ma'am. Can you estimate how much I weigh? It's fine.
Be rude.
It's okay. Be generous. It's fine. Not far. Not far. Not far. 63. Anyone else? Anyone else want to guess how old I am? I'm not 68. No, you're very far off. I need to come closer.
45.
All right, I'm 40. Okay. All right. So what we did here was remote monitoring. You didn't come here and you put a tape against me. You didn't put me on a scale. And you didn't look at my passport, right? And no one came up close and did these measurements. You all did this through what God gave you, with your own eyes. Everybody's remote monitoring everybody. Except, and he's the best of them. And we're all trying to do the same thing to the earth. Except that we cannot go up there because we cannot breathe up there. And we don't have enough human eyes on the planet to be able to look at the totality of the data that we have available from satellites. And we want to be up there. Why? Because it's a really good vantage point. Because it gives us a really nice overview of the entirety of Zimbabwe or the continent. I think, I'm going to give you a little bit of an idea of what these sensors are about. Satellite imagery is not like conventional photography in quite a few ways. Now, here's another game for you. Have a look at focus on the left picture first, and then try to count in your head how many buildings there are on that green rectangle. Just count them. And then try to do the same thing on the right picture within the green rectangle. Now, with which image do you think it's easier to count the buildings? Obviously, on the right. So that tells you the importance of resolution. Resolution basically means how much information is within each pixel. Low resolution images are useful, but high resolution images are better. And in what we're trying to do here for foundations is that we're using a particular type of imagery from a company called Planet, and there's a daily coverage around the Earth with these kinds of high resolution images. So this will be really useful for discerning the types of crops that exist in the farm, but also because it's daily coverage, we can see a more granular evolution of how these things grow. That's not me, huh? That was me. Snooze. Sorry. A typical image is like a normal photo, yes. A typical satellite image does have some similarities with a photo in terms of it does have a width and a height, and there's some pixels in it. But there are many more colors in a satellite image than an unconventional RGB image. So in an unconventional photo on your phone, you have red, green, and blue. And the combination of those gives you this sort of like the sense of color. A similar thing happens in satellite images, except that we have more colors. What does that even mean, right? I'm going to explain to you. So this, in recent times, scientists have managed to understand the nature of light. Light, as we know it, what physicists call it, electromagnetic radiation. Radiation is a scary word, I know, but Basically, X-rays and microwaves and radio waves, they're just light, actually. They're all manifestations of light. Except that in everyday language, when we say light, we actually mean that very little band of the electromagnetic spectrum that we see with the human eyes. So we human beings have been allowed, endowed, to observe light in a very, very narrow part of, the whole spectrum. So light, as it exists in reality, is much more complicated. Now, but what satellites can do is that they allow us to capture photons outside of that very narrow window. And the Earth is constantly emitting light in all kinds of frequencies. So it's important to have these machines up there in space that captures light that we humans cannot see. So we have these bands, and we also have these revisits. Revisits is like the satellite coming in around the Earth daily, capturing the same location every day. So this is the nature of the data. It's very multidimensional. It has, it's very complicated for a human being to look at it just with their own eyes. They will not be able to understand what they're looking at. And that's where AI comes in. Also, I want to touch on something that Dan said earlier. There's two main types of satellites up there. One is the passive sensor. This is a passive sensor. It's just something that takes, just receives light that comes from the sun, that bounces off the ground, and then is captured by the satellite. So this is your conventional optical satellite. It's passive. Basically, it's passive light. And unfortunately, that kind of sensor cannot see through the clouds. But in Aspia, we have invested quite a bit of resources to be able to convert a cloudy image into a non-cloudy image by combining optical data with radar data. What is radar data? Radar data is using microwaves. As I said earlier, microwaves are part of the EM spectrum, the electromagnetic spectrum. But what is special about microwaves? Microwaves can penetrate the cloud. And a radar satellite is an active sensor. It's not a passive sensor. It's an active sensor in the sense that it emits its own light. It's like, basically, imagine the thing having a light torch shining down on the Earth, except that it's not your typical visible light, it's microwaves. It's shooting down those microwaves on the ground. Don't worry, they don't bake you. They're not that type of light. And then they bounce off an object, and then the way when it bounces off the object, it changes the properties of the microwave, and that is detected by the machine. And therefore, a radar image can tell you a lot about what is on the ground through the clouds. It tells you something about the morphology and the shape of the land. Whereas color images, like optical data, tells you a little bit more about the texture and the signatures, the color signatures of material. Radar data tells you a lot of things about the shape, so it's very good for detecting vegetation and the heights of crops and stuff like that. So if you marry it the right way, you can do clever things like remove clouds, and eventually we're planning to use radar data also for foundations. Okay, I have 10 minutes left. And there's also another type of sensor which is not space, it's not orbit, but it relies on planes or drones, and that's very high resolution. But unfortunately, the range is not very good because it has to be local. Eventually, they run out of fuel or battery, so we're not gonna. So, why do you need AI? Is because, as I said, the complexity of the data is so high. We don't have enough human eyes on the planet to look at it all the time. We need to somehow automate this task, this menial cognitive task. And if we combine it with what we call geographical measurements of what we know farms are on the ground, now we can focus our attention of the AI on these particular farms. The other problem about optical data is clouds, as I said. Sometimes, what you see here in red is a particular plot, and that's a satellite image on the left, and on the right is just where we detect clouds. So we can tell the AI where to focus on to avoid the clouds, and because certain parts of the year are so cloudy, it's really important to have a daily coverage, if not more. And again, PlanetScope data offers you that kind of ability. What you see here is the cloud cover of the average image taken in a day with PlanetScope. And between December and March, you have very high cloud cover. So if you have a daily coverage, the chances that you're going to find a relatively clear day are much higher. So this is why it's important to have such a dense collection of satellite images. So as I said, there's not enough human eyes on the planet. The AI is able to deal with very complex data, so it can make our lives easier. It can act as a complementary service to a system that has existed for millennia. Humans have honed a system that just works. It doesn't need to change. If it's not broken, we need to change it. And what we're trying to do here is that we're trying to come in and help that system. I'm going to now build the third pillar. We've talked about sensors, I've talked about AI, and I want to talk about eventually what we want to do with it, right? So I've been observing what you guys talked about, and I think your mission really is part of a much bigger picture about sustainability goals, sustainable development goals. I don't know if you've ever heard about those, but there's quite a few of those things that are being checked by what you're doing here. Our contribution to this is to do three things. Estimate the planting date of a crop, the yield, and the crop type. As to the planting date, imagine, so the circle on the right is the year. In how many days in a year? 365 days? How many degrees in a circle? 360. Is that a coincidence? I don't know. But it's nice that we can use a circle to represent the year. So imagine the green arrow being the correct. Imagine that the green arrow represents the true planting date that you have in the field. And what we're trying to do is that just by looking at this treasure trove of data, this video basically of a farm, we're trying to get the AI to tell us, to estimate when the planting date is. So we're trying to basically get it down to that very narrow green window around that green arrow. That's what we're trying to do. So our margin of error, let's say the bare minimum that we're trying to offer, is plus or minus a week. That's how narrow of a window we want to get to in order to be successful. I promised my colleagues that I would not show you a graph, but I want to just give you an idea of the progress that we've made. What you see here is I just started training an AI model yesterday, and this is how well it's doing within just 8 hours. So we managed to get the AI to predict the correct planting date plus or minus 12 days. So double the size of that band, but we're getting there. It's going pretty well, I think. I think if we leave it running for a few days, we're gonna crack this one. Crop type, I don't have pictures to show you, but we have worked on a very similar problem in the UK, in a region called Cornwall, where the local council has paid us to estimate the type of a tree. So what you see here is the entirety of Cornwall, which is a part of a region of the UK, and whatever is in green is where the AI thinks broadleaf trees are. So, nailed it. This is what we're trying to do here with crop type, in foundations. And again, on the left, here's another graph. We are getting to the point where within 8 hours, the AI was able to predict 75% of the time the correct crop type. And, I think it's on a good way to nail that problem as well. I can't say the same for yield. I don't have a graph to show you, but that's because I recently realized that in order to estimate yield correctly, the estimation of yield relies on the crop type. Once you have the boundary of a field, you need to know what is the crop type in order to estimate its yield, because sometimes in a field there's multiple crops. And if you don't tell the AI in advance what is the crop that you're interested in, it's going to give you a random number. It doesn't know what is the thing it needs to focus on. So first you need to get the crop type correctly, and then you're in a position to estimate the yield. So it's kind of like a tiered problem. First you need to solve the easier one to get to the more complicated one. So, but we'll get there. How much time do I have? I think it's a good time to close it. Maybe just, I've worked on a lot of different problems before in my career. As I said, I've been working in Earth observation for now 6 years, but I've been doing AI for 16 years. And I love the area that I'm now in. I feel this is the most impactful way for AI that benefit humanity. I've worked on problems with some American agencies like the USGS, where we're trying to estimate water on the ground. And we've demonstrated to the US that we can find water. So this is like an actual image, and this is the water that the AI detects. And if you do this on a daily basis, imagine this is a video. Actually, I can play it. If you do this on a daily basis, this is actual work. I'm not joking. This is really exciting for me. This is back from 2020. If you do the same thing on a daily basis, get a water map, and you do this on a continental scale, that tells you the availability of water resources on a continental scale. For something like the States, that's worth trillions of dollars, I think. It's such a valuable resource to be able to say what water flows in your continent, and then you can do management, like you can say where you can expect droughts or where you can expect floods, things like that. I think this is the kind of power that I'm talking about, that satellite data paired with hard work and goodwill can offer to you. I think I've made a good case for AI.